Okay, today we will go over three math questions. Okay, one from linear kinematic chapter, and then two from angular kinematic chapters. So again, but here, as you can see here, this slide could be too small for you to read, so that I want you to have your slide with you. So when you follow me, okay? Let's start with the orienteer problem. This is from linear kinematics chapter. Okay, the orienteer here, okay, he runs north velocity of 5 meters per second for 120 seconds, okay? And then he moves to west at a velocity of 4 meters per second for 180 seconds. The velocity are given, and the times are also given for to this velocity information. And then provide the graphic solution to show the orienteer resultant displacement. Okay, so this blue line could be the graphic solution for the displacement. And then AP5 is also asking us to provide the trigonometric solutions, okay, for IP5. Which means once you develop this graphic solution, and then you should be able to calculate actual value of this displacement, and then this angle as well. Well, as you can see here, information provided here is not displacement, but velocity. But we have to calculate the linear velocity. Okay, so I will show you how to get the displacement from the velocity information provided. And there are hints here as usual. So as long as you follow the hint, it's not very difficult to solve this problem. But let me simply read the hints to a better idea of how to solve these problems. Hint 1, you have two displacements to add, okay? 1 and 2, right? And then draw the displacements with correct directions, okay? Again, north first and then westward, right? And then connect two displacements tip to tail to visualize the resultant displacement, which is the blue arrow as I mentioned. So this can be graphic solution. Okay? And then we have to do AP3. So we have to actually calculate actual values of linear displacement, which means magnitude of this blue line, and then angle of this displacement as well. Okay? So right here, okay? So here, displacement, okay, D here, and the angle. So these are our values of interest. We have to calculate these two values, okay? And then as I mentioned earlier, but this question is asking us to calculate displacement from the velocity information. There's no displacement information provided, but only we have a velocity information. But as you learn, so hint 4 here. From the relationship between velocity and displacement, we can compute the two displacements. Okay? For example, as you learn, okay? Velocity is equal to displacement over time elapsed, right? But here what you have is velocity and time, right? But we need to calculate displacement. So that in this equation, if you multiply each side by delta t, it will be gone, right? The delta t. If you multiply the velocity by delta t, it will give you displacement. And then this is provided, and it's also provided. That's why we need to calculate two displacements first by using this information provided, and then later, lastly, compute the resultant or final linear displacement. Okay. So again, this is what we have right here. Okay, hint 4. Okay. The relationship between velocity and displacement, and then here, by using this one, so we will be able to convert velocity to displacement. Simply multiply the velocity information by time elapsed. Again, velocity multiplied by time elapsed. So this one is 600 meters, okay, displacement, and then for this one, 720 meters in terms of the linear displacement. And then the next steps will be quite straightforward. So these two are tip to tail, right? And then these are 90 degrees, because north and west, which means these are 90 degrees. If then we should be able to use a vector composition. or the Pythagorean theorem. Into 5. These two displacements are perpendicular to each other, which means it's a 90 degree. Okay, 90 degree. And use vector composition or Pythagorean theorem to compute the resultant displacement. Okay, first of all, D here, let's calculate the magnitude of this displacement. Okay, again, since these two are perpendicular to each other, can use vector composition, right? The square root of this one plus the square root this word plus this word, and then do this vector composition. It will give you a 937.323 meters. And then once you get this, right? And then this is once you get this is our angle of interest, which means if that this one will be this one will be so opposite. So that you can again you can use inverse tangent function to calculate actual angle from function value. Okay? So inverse tangent of, again you can use inverse function to calculate angle from function value. So tau r, so opposite of adjacent, right? So opposite of 270 over adjacent. So if you use a calculator, okay, so inverse tangent of this value, okay, if then you will be able to get this 50.19 degrees, okay? And then, but lastly, don't forget to add a directional term, which is this. Because he moved north and then west, which means we are defining this angle from the north toward where? West. That's why in terms of definition of this angle, it must be west of due north. West of due north. Okay, so don't forget to put this directional term information. Okay. And then if you have any questions, just email me, or I'll be online. So during the class time, just you can leave a kind of the note there. And then 2 questions will be coming from angular kinematics chapter. Okay, chapter 11. So if you go to the textbook chapter 11, you will be able to see these questions. Okay, 2 questions. This is from AP2, additional problem number 2. Okay, so this is about the David and Goliath. Okay, David is rotating the sling, and then release a stone to kill the Goliath. That's what it is. Okay, let me simply read the question to let you better understand this problem. Again, this could be too small for you to read. Please read here, so just slide to follow me better. So David is fighting Goliath. Okay, if David's 0.75 meters sling, okay, radius of sling is given, right? This sling is accelerated for 1.5 seconds. Okay, time is given. Okay, at 20 radians per second square. Okay, radians per second square. This is angular acceleration. Okay, what will be the initial velocity of projectile stone? Okay, here we have to calculate the initial velocity of the stone. Okay, when the stone was released from the sling. Okay, so initial velocity means this is actually the tangential velocity when the stone was released, okay, from the sling. So I can visualize the sling here, okay? If the sling will be rotating, okay, about this point, which means this was actual rotation, okay, stone here, and then initial position, and then final position. This is by the time or when the stone was released, okay, from the sling. And then we got this information given, angular acceleration, right? Angular acceleration, and then time information also given, and then radius is also given, the length of this sling, right? So by using this information, we need to calculate the tangential velocity at the stone release right here. So this is a 2-step approach, okay? So, and also this is a question about the relationship between angular kinematics and linear kinematics. So as you learn in the classroom, you can relate so linear kinematics to angular kinematics, because whenever we do anti-motion, okay, linear motion, angular motions, they are occurring at the same time. That's why you can relate these two, right? So again, this is a relationship between linear and angular motion, which is again was part of your second reading assignment. Okay, there are 2-step approach here. Okay, first step is compute the angular velocity of the sling at release. Okay, We calculate angular velocity first, angular velocity, and then compute the linear velocity of the stone at release. Okay. Let me to remember this. Okay. Okay. Tangential velocity. Okay. Linear velocity equal to r times omega. So angular velocity. Angular velocity. And then tangential acceleration, linear acceleration is equal to again radius times alpha angular acceleration. Okay, so you can relate a linear to angular through the radius. So we will be utilizing this relationship to calculate this question. Okay, step 1, compute the angular velocity of the sling at release using the acceleration equation. Okay, so again, let's revisit this one. Okay, so again, these informations are given: angular acceleration, time, and radius. And then, so here, angular velocity of the stone at release means angular velocity at here, which means final angular velocity. Final angular velocity. I can say omega 2. Omega 2 means the final angular velocity, and omega 1 is the initial angular velocity. Although this is not given in the question, so you should be able to find this initial angular velocity information. The stone stopped here. That's why initial angular velocity of the stone must be what? 0 radians per second. Okay? And then okay, this angular acceleration equation. Again, angular acceleration. Okay, as you learn, alpha is equal to the rate of change in angular velocity, which means change in angular velocity over time elapsed. Okay? The time taken from here to here will be 1.5, right? And then initial angular velocity is 0, okay, 0. Okay. And then, okay, angular acceleration also provided 20. If then, you can multiply each side by 1.5, okay? Cancelled out, so 1.5, okay? Multiply this, it will be 30. It's angular velocity, right? 30 radians per second, okay? So we got this final angular velocity, which means angular velocity as stone release. Okay, so here 30 radians per second right here. Okay, but actually the variable of interest that we're going to calculate is actually linear or tangential velocity at this point. Okay, if then that can be the second step. Step 2, compute the linear velocity of the stone at release using a relationship between angular motion of the sling and then linear motion of the stone. Okay, this is something we just calculated, 30 radians per second. So angular velocity at this point, right? And then, so then we got r here. R is a 0.5 meters, and then we just calculated what? Angular velocity, ooh, right here. So 30. If you multiply these two, so it will give you, okay, the linear velocity of the stone at release here. Multiply these two, answer will be 22.5 meters per second. This is the linear velocity, or the tangential linear velocity. Okay. Again, so if you have a question about this one, just let me know or email me, or so I will be online in the class time. Okay, the last one. Let me go over one more. Okay, this is AP5. This is problem number 8. Okay, from chapter 11. This is cyclist. Okay, let me simply visualize this one first. Okay, this one. Okay, cyclist. This is a track for the cycling. Okay, the cyclist enter a curve of 30 meters radius at a speed of 12 meters per second. Okay. Okay, radius this circle is provided. Okay, 30 meters. And then at a speed of 12 meters per second, when he enters this curve, his velocity was 12 meters per second. So his linear velocity. So V1 is his initial linear velocity. And then as the brakes are applied, so when he moves after this move curve, he has to slow down, right? And then he has to apply the brakes. So as brakes are applied, speed is decreased. Okay, you will be slowing down, right? Decreased at a constant rate of 0.5 meter per second squared. Okay, you will be decreased at a rate of 0.5, constant rate of 0.5 meters per second squared. This is the linear acceleration. If then what are the magnitude of the cyclist radial and tangential acceleration when the speed is the 10 meters per second? So when the speed will be decreased, right? Progressively. And then by the time right here, assume that at this point, his speed is 10 meters per second. Okay, when he is here, okay, at 10 meters per second, okay, what are the magnitude of cyclist radial and then tangential acceleration? Okay, so as you learn from the class, so there are two accelerations. Whenever you rotate something, okay, or rotate like this, okay, so joint center will generate angular motion, and any point on this rotating body will experience a linear motion. That's why we can relate these two. So again, tangential acceleration and then radial acceleration. Okay, there are two equations for each one. Okay, for this one, first of all, are the radius times angular acceleration, or v2, v1 over time elapsed. Okay, you can use either this one or this one to calculate the tangential acceleration. Okay, if you are not familiar with this tangential radial acceleration, please go over the angular kinetics slide. Okay, that's your job. And then there are also two equations for calculating radial acceleration. Okay, so r times omega angular velocity squared, or v squared over the radius. Okay, again, you can use either this or this to calculate radial acceleration. Again, depending on which information is provided, okay, you can use either this or this or this or this. Okay, but in this question, there's one information, very important information is already provided, which is so 0.5 meters per second squared. Okay, so let me read this one again. As brakes are applied, okay, the speed is decreased at a constant rate of 0.5 meter per second squared, which means actually the meaning of this one is tangential acceleration, which means in this question you don't have to calculate the tangential acceleration, it's already provided. Okay, then this one can be gone, right? For this question, okay, can be gone. So tangential acceleration already provided, right? As I mentioned, AT, tangential acceleration is equal to negative 0.5 meter per second squared. And then calculate radial acceleration. Either using this one or using this one. Okay? But here, since we already provided with the linear velocity at this point, which means v2, final velocity of this cyclist, so that we need to use this one, which is actually this one, v squared over radius. Okay, because there's no angular velocity information is given in this question. That's why, okay, we need to use this. V2 is what? V2, so 10 meters squared over radius 30 meters per second. So AR will be 3.33 meters per second squared. Okay, so we got tangential and then radial. Okay, and then as you learn, as you can see here, tangential will be acting this direction, right? And then this is the actual rotation, okay, rotation center. And then radial acceleration is always pointing toward this part, toward this rotating the center. And then tangential direction is always perpendicular to direction toward this rotation center, which means these two are perpendicular to each other. Which means, so I can visualize these two. If you get tangential here, okay, 0.5, it's 0.5 meters per second, and then, okay, this is radial, okay, tangential, radial, 3.33 meters per second squared, and perpendicular to each other. If then, so you can move the tangential from here to here, right? As you know, okay. So these two are the same, because I didn't change magnitude or direction of this actually vector. So they can move this vector from here to here, then negative 0.5 meters per second squared. Okay. Still perpendicular to each other, right? Still. If then, okay, tip to tail. Oh, if then, okay, we can connect these two. Okay. This blue one will be, I can say, resultant or total acceleration. Which means once you get these two, which are perpendicular to each other, and then you can get one more step further. Okay. So again, these two perpendicular to each other, you can simply do, I can say total. Okay. The square root of 3.33 squared plus negative 0.5 squared. And it will also give you the total acceleration. So for the exam, once you get these two, tangential acceleration, radial acceleration, and then you should be able to calculate total acceleration too, because these two are perpendicular to each other. Okay? And then we just went over today 3 questions, math questions. And then actually there one more, okay, which is coming from your extra credit assignment. So there might be 3 or 4 math questions in the second exam. So as long as you clearly understand all 3 questions that we went over this one, as well as the extra credit problem, you should be okay for the math questions. And then let me know if you have any questions about this thing. Again, I know this is maybe blurry or invisible, but this is all the best I can do, because the university SRC is closed. This is a biometrics lab, as you know. But I try to upload the video clip in here, so that since okay, this is too small or maybe slightly invisible, you do better have the slide video every time. Okay.